All right, welcome everyone to the UNEP Webinar, Modern Technologies in Combating Disasters on a Hotter Planet. To remind you all, there is a pre-webinar survey that has been sent out, and Paula is going to put it in the chat here, that we would like all of you to fill out before the webinar, just so we can kind of get a sense of who's attending and look at the pre-survey, post-survey, and figure out what we've learned from the webinar. We're excited to bring you this webinar about an extremely interesting and relevant topic. Today we have 4 speakers who will be presenting their work. Before we start, just some technical items. Please keep your microphones and cameras off so that we can focus on the speakers of the webinar. If you have any questions, go ahead and put them in the chat, and then afterwards we will have a Q&A session to address those questions. Just to give some background to this webinar, this is a webinar coordinated within the Modern Technologies and Disasters Management Project, which supports the Disasters and Conflict branch within UNEP. I'm currently an intern within this group. This project focuses on how artificial intelligence, or AI, drones, robots, and Internet of Things can be used to support environmental efforts related to disasters and conflicts. With AI being the ability of a digital computer or computer-controlled robot to perform tasks commonly associated with intelligent beings. This topic was chosen because of the extreme summer that we have just had. The summer showed us how extreme heat can lead to wildfires, drought, and damage to buildings and infrastructure from the extreme weather. Without further ado, I'll give a quick introduction of who will be speaking at this webinar and then give a more detailed intro later. So for opening remarks, we are joined by Andrea Toretti, who works for the Economic Commission Joint Research Center and is a chair for the Modeling Working Group in the focus group on AI for Natural Disaster Management, which he will be discussing in his remarks. We also have Dr. Anshu Sharma from the SEEDS program in India, who will speak to us about using AI to detect damage and building resilient cities in the face of a changing climate and more natural hazards. Next, we are joined by Maria João Souza, a PhD student at Instituto Superior Técnico, Universidade de Lisboa, and research fellow who will be speaking to us about her research detecting wildfires using robots. Finally, René Vogt, the co-founder and CEO of Sensoterra, will talk to us about his goal or his work detecting soil moisture levels and optimizing irrigation. So Andrea, you can get us started with your opening remarks. Let me just stop sharing my screen.
Thank you. I'll now try to share my screen. Okay. I hope you can see my screen. I'll give, yes, thank you. I'll give a very brief overview and on some points to open this session on the use of artificial intelligence for natural disaster management. So, what is the challenge? The challenge that natural hazards are posing to socioeconomic and natural systems are really difficult to handle, and we have been experiencing this year just an example of what might happen more and more often in the coming decades due to climate change. Europe, as well as several other regions of the world, just to mention a few, East Africa, China, South America, they suffered and they have been affected by extreme drought, heat waves, wildfires, floods. The European territory, just to give you more the feeling, more than 60% of the European territory was affected by an extreme drought that in some areas of Europe started already in winter 2021. And that was combined then by a sequence of heat waves starting really early in the season already in some parts of Europe in May. And now also several areas of Europe have experienced floods, flash floods, but also parts of, as you might have seen, the regions of the world such as Pakistan. As I was saying, in 2022, the extreme drought event that affected more than 60% of the European territory caused big challenges, for instance, in terms of water supply issues, dike stability, but also it affected river transportation, the energy sector, not just for hydropower generation, but also for cooling the other power plants, and clearly also the agricultural sector. Crops such as grain, maize, soybean, sunflower, rice have been heavily affected by the extreme conditions that Europe has been experiencing this year. It also connected with, for instance, seawater intrusions in some rivers delta, such as the Po, where the seawater reached on more than 35 kilometers inland, causing indeed damages to the agricultural sector, but also to the ecosystems. What is the role of the AI in all this study? Well, basically, when we are dealing with extreme events and natural hazards, we need to work with huge amount of information coming, for instance, from meteorological observations, sectoral information, for instance, from the agricultural sector, the energy one, remote sensing data, so from satellite, but also we have model simulations and statistical approaches, expert-based media. And we are asked, of course, to evaluate all these sources of information to then define a set of actionable information that can be delivered, thus to enhance the preparedness and reduce the impacts of natural hazards, including, I mean, as for instance, we have seen this year in Europe. That's where AI can play a key role. For instance, in improving and enhancing the way we are currently detecting and tracking extremes such as drought and heat waves, but also in understanding and predicting how these events develop and how the way these events are affecting socioeconomic as well as natural systems. And finally, also to develop new approaches to better evaluate the multi-hazard and multi-sectoral risk posed by such extremes that are often coming as compound and concurrent events, such as it happened this year in spring to summer. And that's why it explains why the initiative, the ITU WMO UNEP initiative was launched, the focus group on AI for natural disaster management, with the idea of really indeed addressing this challenge by thinking about all the three main, let's say, components of the application of AI when AI is applied in the real world. So about data collection, so the way we can use and make clever use and optimize use of all the data we have available, all the information, but also in terms of model development as well as model deployment. And the focus group is going to meet again in late October in Athens in Greece from the 24th to the 26th. But of course, the focus group is not the only initiative that is currently dealing with the integration of AI into existing system and the use of the AI. So we have other big initiatives, for instance, the one launched by the European Commission that is called Destination Earth, that is aiming at creating a digital replica of the Earth system that will indeed enable to develop really innovative ways to model and to then predict and understand all the natural hazards. But also to there are also ongoing projects in the frame of the Horizon 2020 program, such as CLINT, dealing with the integration of artificial intelligence into climate services to provide a much better service, focusing on extreme events such as drought and heat waves, but also XIDA on detection and attribution of climate extremes enhanced by artificial intelligence. Thank you. I hope I gave an overview of what is happening in in this period with respect to AI and natural hazards.
Thank you, Andrea. Next up, okay. The increased temperatures, as well as other climate-related disasters, have been causing buildings and infrastructures damage that they didn't expect because they may have been designed without these hazards in mind. Next up, that'll be our first topic, and it'll be discussed by Dr. Anshu Sharma. Anshu Sharma, an urban planner at the School of Planning and Architecture, New Delhi, did his doctoral research in global environmental studies at Kyoto University. In 1994, he co-founded the civil society organization Seeds in India, which has been working across Asia toward building disaster and climate resilience in vulnerable communities. Anshu has a keen interest in technology and process innovations for disaster resilience and is deeply involved in how modern science and traditional wisdom can add value in making safer habitats and communities. Take it away, Anshu. I'll leave it to you to share your screen.
Thank you, Michael, and hello, everyone. It's great to see a room full of people, some names that I know and a lot of new friends. And thanks, Andrea, for setting the context really well. My work is very easy because now from this context of how AI is a valuable tool in our work on working with disasters, I will walk you through a few live examples of how we are putting this to use in some of our work here at Seeds. I am now sharing my screen and I hope you're able to see it. I'll be talking about a program that we run on using AI for resilience in cities. And to start with, there are three problems where this came from. Firstly, there is a problem of resolution of assessments of risk even within a city. I don't know where you all live, but it's a very common thing nowadays for many of us to be talking about the fact that you make a call to somebody in the same city where you live and you would say, hey, it's raining here. And the other person would say, it's not raining here and it's completely bright and sunny. The variations that you see in the sub-city level across neighborhoods completely defy the kind of warnings we receive or the data that we see, meteorological or hazard-related data, which is uniform. It's at the city level. Often it's even at the regional level. The second problem that we see is in recent years, the changing patterns. So in the communities where we work, which are usually communities on the margins, there's a huge problem of not knowing what to expect, because otherwise there's a seasonality to risk. We know when it'll rain, we know when it's going to be a dry season, when we know when it's going to be very hot, but that's all being disrupted now. And the third problem that we face in these communities is that the information that is received is very difficult to decipher. So if you get to know that it's going to rain 200 millimeters in the next 48 hours, it's very difficult to know what it will do to you, your family, your house. If you get to know that 200,000 cubic of water will be released from a dam upstream from where you live, it's very difficult to convert that into information that you can use. By the way, a cubic would mean a cubic foot per second, which is about 28 liters per second multiplied by 200,000. Makes no sense to me on what it'll do to my house or to my family. So with this kind of a problem set, the project that I'm sharing today is called Sunny Lives. It is an AI model built together with the Microsoft AI for Good lab. And it basically is around addressing this complexity and working around communities and making this user-friendly for application at the community level. The fundamental principle and the image you see here, this is where we started working in 2019. There was a major cyclone on the east coast of India, which devastated very large swaths. And the imagery, the drone imagery and the satellite imagery told us that it's kind of very common sense. And by the way, most of us at Seeds come from a background of architecture and planning. So it should be even more common for us to be able to figure out which houses will stand and which houses won't, just by looking at their rooftops and inferring information, not just about that house, but about the people living inside. So broadly speaking, what happens is there's a lot of work that has been happening around identification of building footprints. So you would see digital data that talks about, every building in the world can be spotted on satellite images, even the kind of image that you see on Google Maps or iPhone Maps application that you all have. So any one of us can pull out our phones, look at the satellite imagery. We've often spotted our own houses. We've seen cars standing around our buildings. The fact is that you can see every building, every rooftop of the world, and rooftops can tell you a lot more than just the building footprint. If it's a very small roof, if it's less than 20 square meters, we would normally infer that there's no toilet inside. If it's a thatched roof, we would infer that it will fly away in a strong wind. If it's a thatched roof, we will also infer that it will probably have mud walls, which will not be able to sustain inundation or heavy rainfall. If it's a tin sheet roof, we would know that it's going to be very hot in the summers, while the thatched roof would have been better off in a heat wave. Now, over the last 3 years, we've been calibrating this. So we install data loggers inside individual houses of different kinds. We simulate, we run a model, we find out where we are seeing differences in the actual reading than what we simulate. And with every cycle, we learn. So what the model now does is, with a fair amount of accuracy, it tells you what impact a certain hazard will have on a particular building and the family inside. And it, in essence, then is converting hazard-based warnings to impact-based warnings. It tells you what this particular cyclone will do to your particular house. That's the precision that it brings. So I'll not go into the details of what and how we score the hazards, the exposure of particular buildings, the vulnerability of the people inside, the materiality, and then a composite risk score. But on the right side, you see how we are able to, for the same hazard along the same riverside, we are able to identify low, medium, and high risk building clusters. Actually, we can do it at individual building level, but we are right now running this at cluster level. The fact is that you can do this manually. Anyone with understanding of how rooftops and buildings and a bit of architecture and civil engineering can sit and do this manually. It would just take you ages to run over a square kilometer or a few square kilometers of an area. With this system coded as an AI model, we can run into large swaths. We can run entire cities in a matter of hours. So the application is that if you get a warning for a cyclone or a flash flood or for a heat wave and other things, you could instantly get to figure out who are the people most at risk so that you can reach out to them. But you can also figure out a long-term approach on how you can help these people, these communities, and these local governments reduce the risk. So this is the kind of a dashboard this leads to. The dashboard ideally will be sitting with local authorities where you will know clusters and you will know priorities on where you need to intervene fast. So far, we've run this on floods, a lot of cyclone-induced floods. We've run it on heat waves. I'll talk a bit about that. And we are now getting into running it for earthquakes too. Now, if you look at so far, we've covered about 100,000 households over these 3 years of piloting. But basically, what we are talking about is early warning, the granularity of early warning that can be improved, the impact it can have on reducing risk through short and long-term measures, and the ability it gives to adapt and scale, not just on hazard-based programs, but for various programs that are influenced by the level of risks that they will see in the times to come. So a scaling strategy, this is where we're entering now, talking to a lot of governments, is that this kind of hyper-local risk mapping can inform ward-level authorities, it can inform urban local bodies. What matters to us is the last mile, which we now in fact call the front, the first mile, is where at the local level, communities, neighborhoods, and households can be benefited by this kind of risk-informed planning. And of course, once you break this down to various use cases, then it goes to a much larger regional or national scale. In the next few slides, I'll give you a few glimpses of how we ran it. This is the last 2 years of work on heat waves. We've been running this in a couple of cities, but I'm showing you stuff from Delhi. So what happens is, for every piece that we take up in this modeling exercise, there's a number of volunteers on the ground, feet on streets, who would be engaged, because our biggest challenge is for the most vulnerable frontline communities to be able to understand warnings and to be able to act upon them. So the volunteer would get this kind of a model output on their phone. And they now know in the hand, you can see the Beat the Heat advisory is an advisory that is a standing advisory aligned to government approaches on steps you need to take if there's a heat wave coming in. What the map on the phone tells you is that, okay, there's a broad heat wave warning for the entire city. For this neighborhood, there's going to be a few clusters and a few houses that are going to be worst hit because the materiality of their buildings, the neighboring areas, the green cover they have, the water bodies that are there, the absorption index of the place is going to create more indoor problems for them than others. So we are now addressing the problem of indoor heat and not so much of outdoor heat, which of course has been going on for long. So with this kind of a tool, you're able to convert neighborhoods into high risk and medium and low risk clusters. And then we engage with communities. We run quiz competitions with kids in schools. We figure out interventions where they can use water, they can use shading devices, they can use insulation on their rooftops, and they can do advisory dissemination locally on what action to take should someone feel the impacts of this heat. This is how we engage with communities on the ground. What I'm trying to basically drive home as a point is that it's the women, it's the elderly, it's the children who are highest at risk. When the ambient temperature in the city is at about 38 degrees, indoors in a tin shack, it can go up to 45 degrees Celsius. I'm talking Celsius, and that's completely unbelievable. And who's indoors during the day? It's infants, it's their mothers, it's older adults, people with disabilities. So that's where we try to take it in a local translated language format. It's done verbally, it's done through these flyers. And lastly, to wind up, as a way ahead, I would talk about the 4 or 5 things where we see this kind of AI modeling generate use cases. And the one that we are chasing very hard right now is to, as I said, get these local communities to own data and to also start generating data. And this is the granularity of the data that actually helps the AI model learn and improve constantly. What you see here in the images is these weather labs that we set up with schools. We started with automated weather stations, but now we are doing more of these manual weather stations, which are very inexpensive. Kids get to see, they're tactile, and they learn a lot through this. And this gets fed into the data system at the city level. We are using the same model to figure out where there's a problem of drainage, where we have disrupted natural drainage channels, where we've eaten up the natural water bodies, and how we can now figure out very quick ways to address this and allow the water to drain across these neighborhoods and cities. We use the same data to go and engage with communities to figure out what kind of innovations, what kind of local knowledge and wisdom can be dovetailed into strategy and can be combined with this data to figure out very localized ways of dealing with the kind of unpredictable risks that are erupting now. We use the same data sets to figure out which water bodies are at risk, which water bodies are being better maintained, and what local interventions can create this kind of water resilience. And finally, we use the same data sets to look at municipal budgets, organizational budgets, to see which line items in a budget are relevant. They can contribute in a good or a bad way to climate resilience in a community, but also which are the ones that are sensitive. For example, green, anything to do with green, whether it's agriculture, we're dealing a lot with urban agriculture, is highly sensitive, whereas a transportation solution is highly relevant, though not sensitive to climate change. With that, I will close just by underscoring the fact that it's really important. It's great. This webinar is around tech, but our experience also shows us that for tech to deliver on the ground, it really needs to have that community engagement interface. So a community-centric and tech-enabled approach is what we would really push for. Thank you so much, and I'll stop here and hand this back to you, Michael.
Thanks for that, Anshu. I'm always blown away by how much we can accomplish by using the satellite data that we haven't had in history. So our next topic is wildfires. So with the increased heat, we've seen an uptick in wildfires, since wildfires are always going to be present whenever there is a combination of dry fuel, heat, and air. Maria Joao Sosa will be speaking about her work. Maria is a PhD student at Instituto Superior Técnico Universidade de Lisboa, while a research fellow at both IDMEC in the Center of Intelligent Systems and at ADAI in the Forest Fire Research Center. Her research interests are in the areas of computational intelligence, robotics, and networked systems. She was nominated for the UN Environment Young Champions of the Earth 2018 prize for her project on decentralized intelligent sensor networks for fire detection and monitoring. She has co-organized several entrepreneurship events, including the international programs such as 3-Day Startup. More recently, she collaborated on the NEAR IPS 2020 workshop side event, monitoring the climate crisis with AI, satellites, and drones, and was on the organizing team of the Tackling Climate Change with Machine Learning workshop at ICML 2021, NEAR IPS 2021 as a lead organizer, and NEAR IPS 2022. Go ahead and take it away, Maria.
Thank you so much for the kind introduction. I will quickly share my screen. Let me know if you're all seeing it,
Yep.
the PowerPoint.
Looks good.
Fantastic. Thank you, everyone. I'm Maria, and I will be presenting this work on building wildfire intelligence at the edge, developed with Alexandre Moutinho and Miguel Almeida in a collaboration between IDMEC and ADAI in Portugal. With wildfires becoming more frequent, intense, and severe, there is an urgency in developing new technological solutions to help detect and monitor these events. On the one hand, it's very important to detect these events in an early stage because frequently ignitions start close to the wildland-urban interface, as we can see on the left. Which presents an immediate danger to communities. And on the other hand, with fires occurring also in large forested areas where fires gain a larger scale fast, monitoring those fires with updated data is also of the utmost importance. In that sense, we can look at artificial intelligence and robotics to provide novel solutions to these problems. And I will contextualize this a bit in the scope of wildfire management. For instance, using image data, how can we leverage AI and robotics, in a sense, in all the 4 stages of wildfire management, such as prevention, where we can use these technologies in vegetation management to reduce fire severity, such as fuel mapping or tracking of vegetation fuel moisture content, preparedness to perform risk assessment concerning environmental conditions, risk mapping, also, on the response stage for wildfire detection and monitoring, which we'll focus on today, and also on the recovery stage, very important. For post-event analysis, for instance, of the burn area mapping, and also for the evaluation of cascading effects such as erosion risks and air quality estimation. As I mentioned, we'll focus on detection and monitoring, which is the work we are currently working on. So for this, our vision focuses on decentralized intelligent sensor networks for wildfire detection and monitoring, namely using networks of sensing agents like high-altitude balloons, drones, and ground-based sensors that can provide mobile infrastructure that adapts to environment changes in real time and can leverage distributed estimation algorithms that provide fault tolerance and allow for a lower computational demand on each agent. These systems, a key element of them is that they perform intelligence inference at the edge, which enables early warnings and real-time monitoring. In this context, our main motivation is empowering aerial robots with AI to detect and monitor wildfires. And for this, we proposed two strategies that have allowed us to make some progress on several challenges, one on the development stage and another on the deployment stage. And today I will emphasize both of those aspects. So the main challenge in working on wildfire detection and monitoring is having access to high quality databases that are large and have a good variety of images. And this is an issue that is somewhat easy to understand and get a grasp on, because if you do a quick search online, you'll find what you can see on the left here, that most of it looks very similar. There's very little variability. It's really variations of pictures of a lot of burning flames. And we are trying to mitigate the effects of wildfire. So we hope to intervene in a much earlier stage. So we actually need data that looks much more like what we can see on the right, where you can see that sometimes you have smoke, sometimes you have clouds, you sometimes have sunsets, and you sort of need to build algorithms that are robust to real world situations. So in this context, one of our approaches focuses on data creation methods and pipelines. So one of the questions we're trying to address is how to build data processing pipelines that, one, enable creating large-scale data sets, and two, include also relevant annotations. So annotations that would be meaningful for the wildfire management task they will be used on. And this sometimes can not be limited to wildfire detection and monitoring, depending on how much information we can extract from an image. So for this, we proposed an approach focused on expert in the loop systems that enable including the experts in the process of developing these algorithms and in development of the data creation process as a whole. And the main goal of this approach is to improve large-scale annotation and that develop data-driven approaches that allow us to create valuable annotations without imposing much energy constraints to the model. So we are really prioritizing having fine-grained performance over processing speed. So we're not very worried about having very fast algorithms in this stage. One example we can give of this approach applied to fire images is some work that we have been doing on fine-grained segmentation. These algorithms and to really annotate one image the best they can and segment the areas of the image with rich information. And what the model outputs result in is created annotation masks that can be leveraged in large-scale learning approaches downstream. So this is one example of this. So the other approach I was mentioning, because the previous algorithms can take quite some time to annotate one image, and if we want to run this on a drone, the algorithms need to have a very high throughput in terms of making running in real time. So the other question we work on is how to build data processing pipelines that, to one, have reduced computational burden, so they are much faster in a sense, and two, are robust to failure modes that occur in the real world. And for this, I would like to get to some of the prep work that we need to do for this, in a sense. So we really need to perform several field campaigns where we collect large amounts of data in order to to experiment different types of conditions, different type of fires. In this image, for instance, we are testing a payload, a sensor payload that has both visible and thermal cameras, and it's hardly perceivable in this image on the top, where you have the fires, but it's very clear that you have 3 fires in the thermal camera, very small ones. So it sort of allows us to test for scale as well in terms of the altitudes and the spatial resolution of the sensors. And for this, our main goal here is to improve the performance in the deployment. So developing data-driven approaches that have significant energy constraints. So the algorithms we use here sometimes are very different from the ones that allowed us to get very fine-grained annotations, because here processing speed is key. While accuracy cannot be overlooked, at least on a coarse level, the detail that we need to get on something that is running on board aerial vehicle is much more reduced in a sense. With this, I conclude my presentation. I'm happy to answer any questions you may have in the Q&A. Also, feel free to reach out to me. You have my email here. I'm happy to answer questions after the webinar as well. And finally, a last word to thank the organizations that have been supporting this research, both at the national level and also from IEEE and NVIDIA as well. Thank you all for your attention.
Thank you for that, Maria. It's good to see imaging AI being used in a way that could help save lives. Switching gears a little bit, drought is becoming much more widespread than it has been in recent history. It is estimated by the UNCCD that by 2050, 75% of the world's population will be affected by drought. Our final speaker is Renee Vogt, who will talk to us about solutions to this and water management generally. Renee is one of the founders of Sensoterra, acting as co-CEO and CCO. He has a degree in geoinformatics and in business administration before moving into the IoT, or Internet of Things, industry in 2016. Renee has held several senior roles in the GIS industry, i.e. ESRI. Before Sensoterra, Renee has founded Connected Green, a platform for sensor-based workflow management for urban green and smart city. With that, I'll hand it over to Renee.
Thank you very much, Michael, and welcome everyone to this webinar. Let me share my screen. As the last presenter on this webinar, I'd like to talk to you about soil moisture. And yeah, as Michael already introduced, it becomes now more and more obvious that we might have an issue with soil moisture. Hence, the reason for my presentation, unseen and underrated. We are actually facing a couple of crises at the same time, right? So what we see is that there's a lot of population growth worldwide. At the same time, resources are dwindling. So farmers need to grow more by using less resources. So the conditions are getting more harsh, but more output needs to be delivered. What we are also seeing, and these are all macro trends, of course, people are attracted by living in the city, right? So populations are growing, but cities have to become, and this is something that we saw especially in the COVID period, cities have to become healthier, greener, and smarter. Now, water plays a central role in all of those developments, right? So what we are currently seeing is that water governance has become crucial. What is water governance? Basically, bridging the gap between demand and supply, which basically means that water management has become crucial. However, and this is a management statement, but it's applicable everywhere. If it's not measured, it can't be managed. So what I'd like to do is to talk a bit more about soil moisture. At the same time, I'd like to look with you at some AI and ML applications which are fed with our sensor data to help basically value soil moisture and make it seen. So actually, only 3% of all water on our planet is fresh water. Only 1/3 of that is accessible because 2/3 is fixed in ice caps or other places on the poles where layers where we can't access it. So only 1% is accessible, and most of the worldwide fresh water is actually in the soil. However, we haven't talked about planetary boundaries today, but soil moisture, and it's a pretty small image over here, but in the category fresh water, we see that soil moisture has already exceeded its planetary boundary. And there are a couple of key challenges which can easily be detected, but they have to be, there has to be a reason why we want to do that, right? So heat and prolonged drought make soil water repellent. What does it mean? It basically means that if it's either dry for a long period and it starts to rain again, the soil is not taking up any water, but it's flowing away, leading to, for example, flash floods. But if it's really hot, this can occur in a matter of days. The fastest time we've seen it was actually in 1.5 days when soil became hydrophobic from normal to hydrophobic. Now there's another big issue, because when soil dries out completely, life in the soil dies. So dry soil turns into dead soil. Well, why do we need soil life? We need it for the structure. Because we need it for the plants to grow, but also structure for nutrition and structure for water behavior. So that's all about the dry part. But wasting fresh water is at least as big an issue as drought. Wasting fresh water is at least a big issue as drought. What does it mean? Over irrigation. So the point that we are identifying here is that the economical value of water is too low. We sell wireless soil moisture sensors, which we have developed in-house with proprietary and patented technology. And one of the reasons why people buy our sensors right now is because fuel is so expensive, but not because water is so expensive. So what's the role of soil moisture in climate change or in climate disasters? What this webinar is all about. Well, first and foremost, plants and trees, they can't thrive without soil moisture, okay? So to achieve optimal crop yields, but also to make cities greener and cooler and more healthy, we need the right amount of soil moisture. Not too much, but also not too few. So optimal crop yields are highly dependent on soil moisture levels in the soil. Soil moisture levels in the fields. And those soil moisture levels have a very narrow bandwidth before it's either too wet or too dry, depending on the soil. The same goes for cool and healthy cities. Actually, if a tree in a city is green, but it doesn't have enough soil moisture, it stays green. So we all think, what a beautiful green tree. However, it's not cooling the city. It's not evaporating moisture, so it's not cooling the city. Also, and like I just already told, both too wet and too dry soils lead to floodings. Of course, if it's too wet, then the whole soil is saturated with water. So if more water comes, it won't be absorbed. But at the same time, too dry soil leads to floodings. And this is something very paradoxical, counterintuitive, but for many people, it's an eye-opener if we talk about this. Wrong practices deplete or pollute freshwater sources. What do we mean with that? Well, most of the time we see farmers and also urban landscapers over-irrigate. Because why? The soil leaves the over-irrigated water, it basically lets it go. So for the farmer, it's not a problem. He puts too much on it, and what's needed stays. But the problem is what's washing out, the water that's washing out will also take nutrients and potentially pesticides and herbicides, or inputs as it's called in the agriculture. But this is going to the groundwater, right? Which then needs to be cleaned again. Also, what we see regarding wrong practices is that it's taken away from one source, then over-irrigation takes place, but it's not coming back to the same source where it was taken away, but it's going somewhere else. For example, in the Middle East, what we often see is that fresh water is actually over-irrigated and then washing out towards salty layers, which is a big issue as well. Degraded land erodes more quickly. So when it's dead, like I just said, and the structure of the land is becoming well, more loose. Let's say it gets a bad structure and it's going to rain, or there is a flooding, the erosion will be a much bigger issue. And then finally, and this is what was already said in the introduction, that air heats up more quickly over dry land. So this is what we've seen in Europe and what we're seeing in China right now, what we've seen in North America, that once soil is becoming dry and it stays hot, that the effect is actually amplifying itself. So dry soil leads to hotter air, leads to more impact, leads to more heat waves, leads to more heat in cities. So we think that soil moisture has got a very big role, plays a very big role in climate change, and it's a pity that it's so often unseen. Well, because what we most of the time see, if it's about AI and modeling, it's about satellite imagery, which you see here on the left side. This is a satellite image of a piece of land of a farmer, where we can see basically the satellite detecting drier and wetter areas. And at the same time, on the right side, we see someone here putting a groundwater probe in a tube. Now, what's often happening is that groundwater and satellite data is used to model soil moisture. So groundwater and satellite data, but it basically means that if your groundwater is -2 meters, and your satellite data can maybe only penetrate the top 10, maybe 20 centimeters of the soil, there's a dark area in between, which we call the missing link, which is soil moisture, which should be measured. Why do we have to act now regarding soil moisture? Well, first of all, we have to keep the soil moisture levels healthy for plants and trees. We have to keep them optimal for absorbing water, which is again counterintuitive. In some areas in the world, farmers are watering their lands before it's going to rain. They're watering the lands before it's going to rain. Why? Because then the water of the rain can absorb more easily. We have to stop over-irrigation to save water and to prevent pollution, hold water where it falls, let it infiltrate or store it to use later. And now I think we're going to look at a little bit of data. We need sensor input for AI and ML. Okay, we need to feed the models with real data. Why? Because in most models, soil moisture measurements are not considered. Why not? Because it's super difficult, and that's what we're going to change, or what we are changing actually. So just a real quick intro in soil moisture science. It's very simple. On the left side, we see that soil can be too dry, it can be healthy, and it can be too wet. If it goes from healthy to too wet, we call that over-irrigation. Why? Because then gravity gets a hold on the water and it washes out, including all the agricultural inputs. What we often see is that there's a lot of focus on under-irrigation, leading to stress, right? So we always say just before we are, there's a point here, it's called the permanent wilting point. Below that, the plants will not be able to get water from the soil. Just above that, you have to irrigate, because otherwise the levels go too low. All right. So why is this so important? If you look to the right, every single soil type has got different soil moisture behavior. So the window, the ideal window, is actually different for every soil. This is also why it is so hard to model. Every soil type needs to be analyzed, and every soil type needs to be processed in a lab to find out exactly what are the characteristics. Now, why is this difficult in modeling? Because it's very hard to interpolate. Okay, that's very hard. Why? The differences in soil are hard to detect, and they are impossible to model, because we don't know what the differences in soil are unless we look into the soil, which means that local knowledge is essential for interpretation. And there's always the discussion about absolute values versus relative values. So as I've just shown you the diagram, which shows that when soil becomes too dry, when it becomes too wet, those are absolute values. This is really not shifting, and it's not really debatable, because certain soils, you are over irrigating over the 28%. Of course, you can look at the relative values, and you can look at graphs and the shapes of graphs, and you can feed that into models. And I'm going to show you some examples of that. However, for now, we need data. Okay, and that's what we're doing. We're collecting, we currently have 12,000 data points around the world, collecting data. And based on that, we can see a lot of things. So here, for example, we see soil becoming hydrophobic. So we see a soil with a level of around 5%, which is a healthy level. What we then see is that there is a very big watering. And what we often see that after a big watering, soil is drying out more quickly. So in a couple of days, it's going basically lower than the line it had before the watering. What we see here is soil becoming hydrophobic, because look at the next watering, it's even going down quicker until it's almost zero. So this is a soil which gets watered. Now, the answer to this I will show you in a minute, which is actually giving less water. So how do we feed it into models? Well, so this is another example, by the way. This is soil, and here we see waterings, but in between those waterings, the soil completely dries out. Now, if we would feed this in a model, of course, and the model knows that soil moisture is at zero, the model knows that the soil is drying out. However, if we would only look at the relative graph here, that would be very hard to detect. Now, this is an example of controlled irrigation, and what we see here is predictive irrigation, which is, of course, the best we'd like to have. So what this means, we are irrigating, and basically we determine the length, the duration of the next irrigation. We base that on where we are in the graph, what the trend is. So here you see these little adjustments of the predictive irrigation. Now, this is a typical example of over-irrigation, and by using this technology, we have got some great results. For example, I will show you this later with the municipality of The Hague over here in the Netherlands. But this very steep peak is showing over-irrigation. Why? Because it goes down almost as quickly as it goes up. And I've made a little orange line here, and this is basically how we teach our algorithms about how to detect these moments of over-irrigation. And look, the second one is how we like to see it, which is a smaller irrigation. And what we see here is funny, right? Because this one goes almost twice as high, which basically means that we put twice as much water on the first graph than on the second graph, but the time that it's taking to dry out is a lot longer. So over irrigation is really a big problem. The last one I'd like to show you is this one. And this is why we need models. This is why we need AI, because this is a healthy soil with healthy levels, around 10% soil moisture. Now, some organizations, they work with calendars. So on the calendar says, okay, half April, we start with irrigating. So basically what we see here, there was an irrigation moment here. But what happens then is that it was over irrigation. So then gravity gets a hold on the water in the soil, and actually the level plunges down further than it was before the irrigation. So what would be the result? What are we telling the model here? Just don't over irrigate if it's like this. Sorry, don't irrigate at all if it's like this. Okay, one more, finding the right balance. If you look at irrigation more than once a week, we see the trend line going up. And if we go to once per week, we see the trend line slightly going down. But it's important maybe that the line below here is more horizontal, right? So the trend in water wings is going down, but the trend, the general trend here is staying the same. All right. Well, let's look at some savings of using this technology for real applications. In the municipality of The Hague, this has been used. They are watering around 1,500 trees, which they plant every year. They water those trees for 2 growing seasons, which means they basically have to water 3,000 trees for a period. For every growing season. And by using this technology, they have saved 1.2 million liters only in 2020. And then the next one is maybe a little bit more impressive if you let the numbers work into your mind, because with our partner Smart Farm Sensing, we are monitoring date palm plantations in Abu Dhabi, and we have been able to save 600 liters of water per tree per week. Now, what's interesting, in the whole MENA region, Middle East, Northern Africa region, there are 80 million of these trees. So 80 million times 600 liters, hypothetically. All right, so what we say, we don't sell sensors, we sell water conservation. Thank you very much. I give the word back to Michael. And then it's maybe time for some Q&A.
Yep. Thanks, Renee. Yeah, to me, soil conditions, they seem very underappreciated as a hazard. And, if they're not managed properly, they can have disastrous consequences. Yeah, so next we're going to be jumping into the Q&A portion of the webinar. Just to reiterate, to submit a question to the speakers, go ahead and use the chat tool on Zoom. If the speakers could turn on their cameras, and then we can get started here. Looks like the first question is to Maria. So this is in regards to local knowledge and ground monitoring. Could this be used to supplement AI-based wildfire early warning systems? And maybe elaborate on how they could be used to ascertain wildfire incidents.
Yeah, absolutely. Local knowledge is fundamental on this, and AI is sort of a means to supplement local knowledge and the civil protection agencies, the firefighters teams, mostly on a response stage. An important thing about AI in this context is that one could think that one could favor having algorithms that are good at detecting, but maybe throw some false positives sometimes. And that's the part where for this technologies to be useful in the real world, we also need to keep the false positives down. Otherwise, the response teams won't be able to trust these systems if they have to respond to AI-based warning that then turns out not to be a real one. So local knowledge is very important, particularly in the context of ground monitoring, because as we mentioned, we mentioned the stratospheric low altitude with drones and the ground-based, but we also have the satellite data that is important, but all these solutions have very different temporal scales. Some we can have almost in real time, some we can only have every hour, some every day, so it changes a lot. And ground-based solutions, particularly when we talk about villages, the well-learned urban interface, it's very important, because odds are that the fires will be detected either by people or by cameras installed on infrastructures there. For the cases where we're talking about very remote areas, the satellites and, for instance, the high altitude balloon solution might work best for those cases.
All right. Okay, our next question is for Anshu. You spoke about floods, heat, and earthquakes. Can the model also be deployed for other use cases?
Yeah, thanks, Michael. Absolutely, yes. I think what cuts across the presentation that Renee, Maria, and I made is that we are using tech to calibrate an input in one of the pipelines. And even the response that Maria just gave is there will be, if you look at the complete system of what informs people and responders in reacting to a situation, there will be multiple inputs. For example, there will be inputs from local communities and their wisdom. There will be inputs from meteorological data. There will be inputs from surface data, whether it's river monitoring for floods or it's soil moisture monitoring that Renee spoke about. So the fundamental thing we are talking about here is that anything that you are able to manually decipher as an upcoming risk or input factors to risk can be taken up in an AI approach to scale and to improve the speed. So as I said in my presentation, we are doing this right now for floods, for heat, and for earthquakes, but a constant conversation is what other use case that can this go into. And one, of course, is fires, forest fires that Maria spoke about. Right now, we are looking at this in isolation, but if you put these together, a seasonal diagram tells us that heat, forest fires, and water stress come as a package, right? So, and that's the logic we will need for deploying AI. I would say it can go to any use case. If we speak to local communities around what risk they perceive, no matter what that is, to the fact that we are even trying to deploy this on issues such as social exclusion and social risks. If there is granularity that can be brought about in the way we perceive risk, absolutely yes, an AI model can support it. Michael?
All right. Our next question comes from Judy. And I'm going to direct this one to Renee to start with, but I think you know, the other two speakers can also chime in here a little bit. How can AI be used to measure grasslands or rangelands for drought risk, whether it be water stress or wildlife risk?
Yeah, I think that's a very good question, and I actually fully concur with what Anshu said just before me, that if you think about wetlands or grasslands, I mean, it's important that they have, you know, that they are not too wet and especially not too dry. Now, terrain variations are most of the times influencing the soil moisture levels very much. So what you see, if there's, for example, a slope or a hilly area, this leads to more dry patches of grass, for example. Now, the problem with vegetation is that if you can detect something, you know, if you can detect from a satellite image that vegetation is in stress, you're already too late, right? Because it has already, you know, it's already in stress mode before you can detect it. So this is why we think that these sensors and the satellite imagery are very much complementary, where we use the satellite imagery to detect where to put the sensors actually, and then to use the sensor data to enhance the satellite imagery. But we'll never be able, I think, to use, only satellite or only sensors. And at the same time, like everybody already confirmed before me, local knowledge is key in this. I hope that answers the question.
And I'll open it up if Ancho, Maria, if you guys have any comments you want to make.
Thanks, Michael. I was just about to jump in. So I think this is a great question because it mentions wildlife also, and two thoughts immediately strike me. One is it may be shocking information for some of you, but on the subcontinent where I'm speaking from, we lose about 100,000 people to snake bites every year. And there are close to 500,000 amputations or permanent disabilities just from snake bites. Snake bites is something we are able to correlate very closely to flooding. Right. So the way the boundaries can be pushed and expanded when deploying AI for risk reduction is completely unlimited. In fact, the starting point, some of the work that I shared today, the starting point was a very small informal meeting among 4 or 5 people, some from the AI world. This was friends from the Microsoft AI for Good lab, and some from Cs who are architects who respond to disasters, right? So when you get the coding people and the architecture people in the same room across a table, it's a completely unplanned conversation that took off. That, we can see buildings. I can see every building on my phone, but then it said, hey, you can only see a building footprint. I can actually tell you about the people living inside. And so how do you do that? And and then there's this theory of the book Blink by Malcolm Gladwell, which says that based on what you've been doing, there's a lot that your subconscious mind tells you, right? So as I said, if it's a 15 square meter house, I can tell you there'll be no toilet inside. Now, if you ask me to publish this in a paper, I'm sure Maria's a PhD scholar and will vouch for it. I will have to spend a day looking for the right references to cite. But having done this for 30 years, I can tell you it works like that. And what we do with AI then is this bunch gets together and they are able to run this over 1,000 houses with ground data, then run it over 1,000 houses without ground data and calibrate and find errors. And over 3 cycles, the improvement is phenomenal. Now, just from an image, we can tell you who has a toilet indoors and who doesn't. And similarly, another conversation we very recently had was when we had this bunch sitting with a bunch of doctors in the room, right? And we are talking about heat, right? So we say that, okay, there's going to be heat inside. And as an architect, I can tell you there'll be thermal discomfort. But the doctor instantly said that there is heat strokes and there is heat stress. I said, how do you define heat stress? He said, blood pressure beyond a certain level, headaches, watering eyes, drop in efficiency. So this person will not be able to work the next working day to full efficiency. A child will not be able to go to school and learn with full efficiency. And they are able to convert this with economists into disability adjusted life years. So in your life, if you're living in a hot slum in North India, then through your life, there's a huge chunk of productivity that you lose. That's something that the society loses, right? So these kind of numbers, and I would urge everyone, the fun, the magic is always outside your comfort zone and your own domain. So when architects talk to coding people, when doctors talk to architects, when people working on social exclusion talk to computer science people, there's complete magic that comes out of it. So great question. I guess more coming. So I'll hand this back to you, Michael and Maria, if you have any thoughts. But I think that the beauty of the question, this question, and where we are heading is there's so much of cross-fertilization that is desperately required. The tool itself can deliver magic. It's up to us what we feed into it and where we lead it. Michael?
Yeah, and Maria, I'll leave it to you if you want to give a comment or not.
Yeah, sure. Thanks. Yeah, focusing a bit on the wildfire management as a whole, there's a lot of opportunities there that tie to this question that was raised. Particularly, I would highlight the prevention stage. That is one that we need a lot of development. But for instance, we could use the same technologies. We could still use AI. We could still use robotics. But for instance, for fuel mapping, for tracking vegetation, fuel, moisture content, we would use a different sense of sensors that will generate different types of data that would bring up different challenges. So I would also second Andrew's point of the cross-fertilization between domains, because this is really important, not only in this climate problems, but in any problem where we're trying to include some sort of artificial intelligence to really bring them into the context of the experts that have domain knowledge of a given field.
All right, well said. So our next question is to Renee. You used AI in the UAE example to optimize palm watering. Can the algorithm you used be adjusted to assess / quantify the soil salinity resulted from drying?
Yes. Well, thanks for the question, first of all, Osama. And it's a returning question, and it only shows, let's say, the issues which are looming around the corner regarding soil moisture and drought. So just as a little sidestep, in the Netherlands, where we are located, we are below sea level. But what's happening is actually that the seawater is coming under the dikes, and it's coming up again in the land, you know, behind the dikes. So we need fresh water to push back the salt water. If there's not enough fresh water like we had this year with the drought, we have big salination issues as well over here, or salinity issues. So this question goes for the Middle East. Well, look, there you already have a lot of salt in the soil. So what happens is that fresh water then basically temporarily takes away the salt, but if the fresh water is finished, then the salt comes back again, and let's say the salt effect comes back again. So we have this very clear in our data. We already have some compensations for it, but we have to collect a little bit more data. So yes, we have it in our algorithms. We are compensating for it, but this is really let's call it a difficult animal. So if anyone has got ideas about that, and there are of course soil moisture sensors with less sensitivity to salinity, but those are more expensive and more, you know, they require more maintenance, so they are not so practical again so far.
So our next question is to Maria. What are examples of difficulties in assessing or actually collecting quality data for wildfires?
Thanks for that question. Yeah, I would say the biggest challenges often come from having the capacity to develop scale experiment that would be representative of issues that come up in a large scale fire. So it's obviously very difficult to deploy these very early stage technologies in a real event, because we could be being very inefficient or having troubles because the technologies don't have a technology readiness level very high yet. So the scale factor is difficult. And another that anyone working on machine learning, artificial intelligence areas might face is actually the stage where, well, how can I find collaborators that can help me into sort of performing these experiments? And this has been one of the great parts of working in the work between IDMEC and ADAI, because ADAI focuses on wildfire research, is their expertise. So we are able to carry out along with them a diverse set of experiments in small scale and even larger scale than what we saw here today in the mountain ranges, where we can burn several parcels, not just for this type of research we're doing on AI, but for a large set of other fire relevant experiments. So the collaboration, because this also implies many costs, is really essential so that we can develop on several fronts at the same time.
Okay, our next question goes to Anshu. How do you capture risks arising from factors other than rooftops?
So thanks, Michael. Basically, I sped through the whole methodology, but from the rooftops, we get very specific data around what's happening in that building and to that structure. But besides that, we use a digital elevation model to figure out how inundation will happen in that area. And we use ground cover. We look at vegetation in the region. We look at soft soils that will help or retard water runoff. And we look at any major water bodies that can influence. So there is an ecosystem approach to it. There is, in fact, 3 pieces: the building that we decipher from the rooftop, the people that we decipher from the building typology and other socioeconomic characteristics, and the ecosystem that we fix on that. I was also noticing, in between there was a comment from Judy, and what I really, I didn't know there are vets in this group, which is so interesting. I did want to be a vet once upon a time. I would have really enjoyed being one and felt very fulfilled. So thank you, Judy. And I think very, very briefly, I had touched upon the issue of snake bites, but when you raised this, the thought that crossed my mind was the UNDRR, the UN Disaster Risk Reduction Office, has been really pushing the issue of animals in a big way. In fact, less than a week ago, earlier this week, there was a tweet, and right now they are doing a conference, the Asia Pacific Ministerial Conference on Disaster Risk Reduction, happening in Brisbane. These are the conversations which we wouldn't hear till a few years ago, and they're very big now. Judy, do look up UNDRR's tweet where they talk about how pets need to be and animals need to be part of disaster management plans in a very big way. And my instant reaction to that was, how will they become part of plans if we don't have data on them? So the moment you allow us to generate and integrate this data, then a lot happens. So Michael, not just about what else we gather, but the potential of picking these things that we can further add to our metric. Michael?
Yeah, and the next question is an open one to all of the panelists and speakers. Many times developing countries cannot afford expensive large-scale computing infrastructure or very fancy tech sensors. How can we solve this issue and make AI and technology available to all communities? I'll let anyone jump in first.
Well, I think that's a great question, which we are already seeing in practice right now, like areas of the world where they just, they need the sensors, but they can't pay the sensors. So I think we can see 3 key developments there. One is, let's say, democratization of data. So let's say letting people work together in societies or in communities together and to share data. So you don't really need the fancy systems, but you get a system that uses knowledge. And that's I think the beauty of ML, for example, of machine learning. You use lessons learned from other places in the world. What we also see, especially in IoT, of course, is that devices are getting cheaper, which is good. So the devices are getting smaller and simpler and cheaper. And I think to my last point, and that's I think the whole theme of the whole webinar is that, I mean, if you are able to create nice models, and then everybody with a phone or with a smartphone, so we see very much creative solutions. But Maria or Anshu, yeah, maybe I see Anshu nodding.
No, absolutely right. I completely echo the sentiment. Devices are getting cheaper, but I think where you were ending, Rennie, the fundamental point is you need devices. What AI and ML is offering us is the ability to quickly learn what the device is doing and be predictive around that, and be predictive with very high levels of accuracy. So in our work, and I can talk about that since I've done it, initial rounds of work, we are installing a lot of data loggers, we are calibrating the model. In the second, third cycle, that reduces, we are taking so in the first round, we were doing 100% sample of ground truthing. By the third or fourth round, we're doing 10% ground truthing. Now we are running at 2 to 3% ground truthing, which is only to tweak, and we are already running at super high levels of efficiency. So the way, the way many of us who are in that age bracket would remember that a couple of decades ago, GIS was a very, very high-end technology and expensive. And to be able to run just a routing system to figure out from point A to point B how you would get took a lot of effort, and it was expensive. Now it's running for free on everybody's phone. So there is an entry barrier, but what I anticipate is that in the coming years, and not many years, I think within the next 3 to 5 years, we would see dramatic reduction in investments required and a dramatic rise in the accuracy of what these models will be able to tell us for almost no investment. Michael?
And Maria, did you have any thoughts on this one?
Sure, thanks. I completely agree. We are seeing this revolution sort of go hand in hand. On the one hand, the artificial intelligence one, but also the miniaturization of technology, where we see things becoming much cheaper in a sense. Of course, in my presentation, I focus on sort of two branches of development, like the development stage of AI algorithms and the deployment stage. And for places where these very large computing infrastructures are not available, there we really have to focus on improving the deployment stage and making sure we scale the resources in that stage. And also that we can, in a sense, as René said, democratize the knowledge and the science about these issues, so that we serve both global north and global south, in a sense, that we can solve, tackle this climate change issue as a whole.
Yeah, well said. So the next question I'll get to is from Jessica for René. Kind of building off of Paula's question, I think, what role can scalable data support governance in enabling water management for disaster prevention, such as flooding from soil sealing and hydrophobia?
Yes, I think, and I think the answer to this is very much to what we, I think, just discussed about how to make data or how to make this available for, more people, and also people in less rich countries. I think that this would be the same. Like if a government is investing in these models or investing, in infrastructure, which then leads to very simple communication. I loved the piece of paper I saw in Anshu's presentation, for example. Like, hey, look, ultimately we talk about AI and fantastic supercomputers, whatever, but if it's a piece of paper that needs to be handed out to someone, then it needs to be a piece of paper. So it doesn't have to be an expensive device or even a smartphone. So what I think is that the government should play a bigger role here, because water is a cycle. And the water that you take away, to water a tree in a city is maybe taken away from an agricultural area, but they don't know from each other. So I know in India, for example, that there are provinces taking a lot of water from rivers so that they have enough water, but then downstream there is less water available or no water available, which is, I think, should be, but again, you can't manage it if you don't measure it.
All right, and then we have a final question here from Osama. Does AI really help in estimating how much water should be used for irrigation to encounter the estimated plume of saltwater intrusion especially at coastal areas?
Well, in short, I would say yes. However, the underlying mechanisms are so complex that we definitely need more data for that, and we need to do a lot of, and this is, I think, what Anshu was also saying, like you calibrate the model with the measurement data, right, with sensor data, and I think that this model almost needs to be derived from sensor data. But yes, it's absolutely possible, and we are working hard to be able to do this, because the salt water becomes the next big issue for freshwater, supplies.
All right, I think that, I mean, with the time, I think that ends our Q&A, and I'll give each speaker, 30 seconds to a minute maybe to give your final remarks for the end of the webinar. Let's start with Anshu.
Thank you. It's been a wonderful time spent with all of you. Very thought-provoking things. I would just like to leave with the final thought that I guess we've sold AI really hard and tech very hard, which is all good, but there's a lot of spaces in which more thought is required. A couple that we are struggling with right now. A prominent one is the ethics of running AI for a lot of our work. As I showed you in some of my slides, we are able to figure out risk levels for individual households. And we are still not very clear what harm it can do if we go public with this information with individual families tagged, which is why all the data that we release or use publicly is at cluster level. So there's this, and there's many other things aligned to the ethics side of using AI. So we need to be conscious. It's a very new field. We need to work this out. There's potential harm on the way that we need to be conscious about. And the other thing that I'd like to leave you with is that there's so much more that we haven't even explored where this will work as a tool. There's going to be magic in this space in the years to come. So please do play in this play field, and we would very keenly be watching what happens in all these streams. Thank you so much, Michael.
All right, and then Maria.
Thank you so much. Yeah, it has been a riveting discussion here today, and it was very interesting for me as well to see all the interconnections between the topics, and that is something that I would like to highlight. Also, because some of the work I don't do on the wildfires is more on the prevention side of the preparedness side that would intersect a lot with the topics covered by Anshu and René as well. So I think it could be a really interesting starting point to look at the intersection of these areas. Thank you all.
And René.
Yeah, what else is left to say? No, I think my final thought would be that we have the technology. We are able to, I mean, water doesn't stop at a country border. Water doesn't stop at a municipality border, and the same goes for disasters, right? And the same goes for droughts. So I think, for me, I mean, I think science is ready. I think the market is ready. For me, it's more like, okay, policymakers and governments need to be ready, or they need to make ready, because they have, I think, all kinds of laws and all kinds of restrictions in place, which are now, I think, hindering these technologies and hindering, let's say, the use of these great tools to make life on Earth better. Why are we still applying those old mechanisms, right? Why are the governments not, I mean, at the forefront here? That would be my final thought. That would maybe more like a challenge. I mean, I spoke with the CEO of a drinking water company here in the Netherlands last week at a conference. I said to him, look, and he said, oh yeah, I'm looking for innovative technologies. I say, yeah, here, I have it for you. You can stick it in the ground and it works. And he said, yeah, okay, yeah, well, But this is for a farmer, isn't it? And I said, yeah, but if this farmer is putting too much water on his land, first of all, he's depleting your fresh water source. Plus, whatever he's over irrigating pollutes your other source, okay? So it's in your interest. And he was really like, oh, wait a minute. Oh, I see someone else over there. Oh, hey, Herman, you know, he just walked away. He was like, okay, he was over. And then someone else came to me. He said, yeah, but look, Renee, you can't blame him because he's got one mission. And that's just pumping up groundwater. And the problem is everybody has got his own mission. And I think we should. And that's the theme of the UN Water Conference in 2023, sorry. Breaking the boundaries.
Yeah, well said. Well said. Let me just share my final slide. All right. I just wanted to thank everyone for joining us and attending our webinar on modern technologies in combating disasters on a hotter planet. Special thank you to all of our speakers for sharing their interesting and insightful work and educating us about how we are using tech to solve our climate problems. An additional thank you to Paula Padrino Villela, who is my manager and the person who has been providing technical support for this webinar, without whom this webinar would not have been possible. Thank you all. Have a good rest of your days, morning, afternoon, evening, whatever it may be. All right, take care, everyone.
Thank you. Bye-bye.
Thank you all.
Thank you, everyone.